Dear students, I welcome you for the today's lecture related to the multiple effect evaporators and its designing aspects. The evaporator classification, the single effect evaporation systems, multiple effect evaporation systems, then thermal vapor recompression and mechanical vapor recompression that is there. The multiple effect evaporators, the forward feed arrangement, backward feed arrangement, parallel feed arrangement, and the mixed feed arrangements are there in the multiple effect evaporation systems. Now, in a single effect evaporator system, it is the simplest one, and where the steam is fed into the chest of this evaporator system. The feed is there. From the top the vapors are going out, and vapors are going out to the condenser, and the bottom is the concentrated product, and steam is there, and steam is getting condensed from the bottom section. This is the single effect evaporator system. Vapors produced are still steam, and thus can be used to provide the heat of evaporation in a subsequent stages. Now here the steam is generated, or the vapors are generated in the first stage. So can we utilize these vapors into the next subsequent evaporator, and that makes the effect, that is the multiple effect evaporation systems. The vapors produced by the evaporation in the first stage are used as this heating media for the second stage evaporators. Since there is no driving force, thus the operating pressure in the second stage must be reduced to lower the boiling temperature. The vapors generated will be the same. Vapors generated in the first stage will be the same as that of the boiling point. For that purpose, we are reducing the boiling point in the second stage, and so that the generated vapors will be useful for evaporation purpose. That means the vapors from the first phase are fed to the second phase steam chest, and the concentrated solution is going into the second stage. So it's a quantities of solution can be concentrated are large, where we use the multiple effect evaporators. There the quantities of the solutions are large. As the quantities are large, so the size of single evaporator will be very huge one, and as a reduce to reduction, as the point of view of reduction in the fabrication cost, a big equipment cost, handling cost, all those costs will be reduced, and so the multiple effect evaporator systems, they are used. Then vapor generated during the evaporation in the single units are wasted in a condenser, because if it's a single stage, we are condensing the generated vapors, and as a result you require a separate condenser, then cooling tower. All these operations will be associated with that condenser. So for that purpose, to increase the economy, the multiple effect evaporator system, the vapors generated in the first unit are effectively utilized in the second unit. That is, the water is boiled in a sequence of the vessels, each held at a lower pressure than the previous one, because the boiling point of water decreases as the pressure decreases. So the vapor boils off in one vessel can be used to heat the next vessel. Generally, the first vessel requires an external source of heat from where we are transferring this heat in the form of vapors generated from the first stage. Vaporization in the second stage and third stage unit is accomplished on the basis of vapor generated in the preceding units. Temperature and pressure decreases in the second stage and third stage, and so we have to apply the vacuum. Vacuum reduces the boiling point of a solution. Even with the lower heat contents of the vapor, evaporation can be effectively achieved. So, to effectively utilize the heat contents of the vapors, the last stage of multiple effect evaporators that is generally carried out in the vacuum. Now, in this multiple effect evaporator system, the backward feed arrangement, forward feed arrangement, mixed feed arrangement, and the parallel feed arrangements, these are the different arrangements that is provided. Now, in this backward feed arrangement, the feed that is entering from the last effect of the evaporator, that is the dilute solution, is feed in the last effect. The feed is in the last effect. This is the first, second, and the third effect evaporator. So feed that is entering into the last effect. No need of the pump is necessary in the last effect, as it is no need of the pump. Here you will not require a pump because this is under vacuum, so the fluid can easily flow. Then, but the pump required in this intermittent steps will be required, as this is at lower pressure and this is at a higher pressure. So from lower pressure to higher pressure you will require definitely a pump. Again, here also from lower pressure to higher pressure you will definitely require a pump. So feed then pump through the successive effects to the first stage. Any feed preheating is done in the last stage. If the preheating is done, it is carried out for the feed before the last stage. Then the thick liquor is produced in the first effect. So concentrated liquor that is formed in the first effect, where the temperature difference is the highest in the first effect. Why? Because the steam that is at a highest temperature here, the fresh steam that is used here, so the temperature difference that will be the highest in this first effect. Then liquor does not flash as it enters the evaporator body. Then the small diameter liquor lines can be used because the pumps, they will be used for supply of the liquor from one unit to the another unit. Then the backward feed arrangement is best for cold feed liquids. If the feed is the cold one, then this backward feed arrangement is the most suitable. Then steam economy for backward feed arrangement is better than the forward feed arrangement. It is similar to your cross flow arrangement in case of our heat exchangers. Now the forward feed arrangement, it's a parallel flow arrangement. So dilute solution is pumped to the first effect. First effect, the dilute solution of the pump, it is you are to use here the pump to transfer the feed into the evaporator. So dilute solution, it is pumped to the first effect. Then concentration of the solution increases from first to the last effect as you move forward. the concentration increases, so concentrated product is obtained from the last effect. No intermediate pumps are required here. No pumps are required because the pressure reduction is there. This is at a highest pressure, then less pressure, and this can be under the vacuum. So no intermittent pumps is required because the flow is in the direction of decreasing pressure. Now one has to think of how the fluid will be controlled. For that purpose, control valves are used to regulate the flow. So in this line, instead of putting the pump, one can use the control valve, and which is going to control the flow rate of the fluid going into the next effect. Then the feed solution may either enter the cold and subsequently require a considerable amount of the live steam to heat it to its boiling point. Then thick liquor, which is sluggish, is produced in the last effect where the availability temperature difference is the lowest. Liquor pipelines can be easily become the steam blocked as the liquor flashes into the vapor body. Then the next is the mixed flow arrangement. This is the mixed flow arrangement. The dilute liquid enters in an intermediate effect. Now in this case of the figure with the 5 evaporators, the dilute feed that enters into the third effect. So flow in the forward feed at the end of the series. So as a result, the fluid moves in the forward feed direction as it moves, and then from last effect it comes back either to the second or to the first, and then from second to the first effect evaporator. So steam is here. Here you can achieve the maximum temperature gradient. In this case, elimination of the pumps that can be achieved, and the final concentration at the highest temperature gradient that will be achieved, which is in a first evaporator. Then frothing and scalings are also claimed to be minimized. Then for example, in case of a caustic concentration, you get caustic soda concentration. The people use these mixed feed arrangements in the industries. Then the parallel feed arrangement. The feed solution is directly sent directly to each effect. That means the feed which will be going is sent to the individual effects separately. So no transfer of solution from one effect to the another. Solution, that is concentrated solution, will not move from one effect to the another effect. But the thick liquor is taken out from each effect. As a result, we have to take out the liquor at from every effect. This is the concentrated liquor. This is practiced in the crystallization processes, for example, in case of our salt industries. Then thermal vapor recompression. The steam generated vapors, they are used back into the steam ejector. And in case of mechanical recompression, the generated vapors are compressed and sent back into the steam chest. Now the calculations of single effect evaporator, that is say now take a balance over this. F, that is the feed which is being sent to the evaporator. Then the vapors that will be generated and the concentrated solution that will be taken out from the bottom of the vessel. This is the concentrated solution. These are the vapors generated. Now it is a simple material balance that we will take. So feed that is entering here and the vapors are generated which are going from the top and the concentrated liquor which is going from the bottom. So F is equal to D plus W. D is the vapor generated and W is the weight of concentrated solution. Now taking the solute balance, a solid balance we are taking. So initially at the inlet, F into the Xi, that is coming the amount of the solids into the system, into the evaporator, that is F into Xi. Are the solutes or the solids leaving from the top? No, only the vapors they are going out. So the generated vapors that will be there, and from the bottom the all the solute will come out and the concentration of this will increase. So which is equal to W into the XF. XF is nothing but the weight fraction of solute in concentrated solution, and weight fraction of solids in the feed solution is the Xi inlet. So this is the simple material balance we have taken. Now similarly, we can have the steam balance also. The steam balance, mass of the steam, and Ts is the temperature, steam temperature. So in this case, considering the feed is at a lower temperature, now the energy required to bring the feed solution to the boiling point and the energy required for the generation of the vapors. So you will require the two energy. One is your sensible heat and second is your latent heat of vaporization that will be there. One is your sensible heat, that means to bring the feed solution to the boiling point. So H1 is the energy required for the feed solution to bring to its boiling point, which is equal to the mass flow rate of the feed into Cp of the feed into the temperature difference, that is Tb minus Ti. Tb minus Tf. Tf is the solution temperature into the vessel. Then the energy temperature of the feed solution Tf. The energy required for vaporization of the water, which is equal to the m lambda, nothing but m is in this case is the D which is going out from the vapors. Lambda is latent heat of vaporization. So total heat of evaporation is H1 plus H2. The quantity of the steam required for evaporation, which is m lambda, which is equal to the temperature difference, and that is considered to be taken as the Q, total heat. Now the steam economy of evaporators, that is nothing but the kgs of water evaporated upon the kgs of steam supplied. What is the output and what is the input? Input is your steam supply and output is kgs of water evaporated, that is the D amount of the kgs of water that is evaporated. So the rate of heat transfer, which is equal to Q UA into the delta T, that is the temperature gradient between the steam and the boiling point of the solution. So from here you can calculate the area required for the heat transfer. This Q is nothing but the total amount of the heat, that is the temperature sensible heat plus the latent heat. Or if the feed is directly at the boiling point, then it is only the latent heat that will be there. So the outside diameter of the tube that can be calculated, the number of the tubes required for the single effect evaporator, that will be calculated as N, which is equal to A into pi dO into L. Here we have to select the outside diameter of the tube, that may be from 50 millimeter to 100 millimeter depending upon the nature of the fluid. Now let us discuss the heat transfer area calculations in the multiple effect evaporator systems. So this is the multiple effect evaporator system, that is C1 is the specific heat of the feed solution, CF is the specific heat of the feed solution, C1, C2, C3 are the specific heat of the liquid from the effects 1, 2, 3. W, that is the total water evaporated, W1, W2, W3, that is the water evaporated with the effects 1, 2 and 3. Then T1, T2, T3 are the boiling points of the liquor. Then F is the dilute feed, Tf is the temperature of the feed solution, Ts is saturation temperature of steam, M is the steam to the first effect, lambda is the latent heat of the steam, lambda 1, lambda 2, lambda 3, they are the latent heat of vaporization in the effects 1, 2 and 3. So one by one we will first we will discuss for the backward feed arrangement. Now this is the backward feed arrangement that is there. Feed is entering at one end. So F, that is the feed entering, and which is at a temperature of the Tf and having a Cp value, Cf Cp of feed and the temperature of the feed. Then this is the third effect. So here the temperature is T3 and the C3 is the concentration from this, and whatever the vapors going out will have the weight W3 and will have the latent heat as the lambda 3. So similarly for the vapors W2 and lambda 2 and W1 with lambda 1. Then whatever the feed which is getting transferred here, that will be the F minus W3, the feed which is going out, or the concentrated solution which is going out from the third effect will be F minus W3. So this much amount of the concentrated solution will be going into the second effect, and which is at a temperature of a T3. So similarly here the temperature T2 and concentration C2 that will be there, and temperature T1 and concentration C1 that will be there. Now in this pump will give the feed minus W3 minus W2, W3 minus W2. These are the vapors going out. So this much amount of the fluid that will be going into the first effect, and from the third effect it is F minus W2 minus W3 minus W1, that will be there. So this is the amount of the feed that will be going. Now what happens to the steam? Steam which is having the mass flow rate m, lambda is the lambda of the steam that will be there, which is at that corresponding pressure, temperature Ts, that will be existing. So this is the configuration of the system that will be existing, and so one by one we'll take a balance of this feed balance on the first effect. So first effect, it is the steam, fresh steam that is coming in. So m lambda, that m lambda s, that will be there. Here it's a m lambda steam, and which is here W1 into the lambda 1 plus temperature difference from T1 to Tf. So this is the amount of the heat, W1 into lambda 1, that will be there. Similarly, heat balance on the second effect, that is, this is the input amount of the heat, W1 into the lambda 1. This is the input amount of the heat, W1 into lambda 1. From the input of this second, that is the F minus W1 into the C1 into the T1 minus T2, which is nothing but W2 into lambda 2. Then heat balance on third effect, that is W2 lambda 2 plus F minus W1 minus W2 into C2 into T2 minus T3, which is equal to the W3 lambda 3. So taking the total water evaporated W, which is equal to W1 plus W2 plus W3. So heat transfer area required in the different effects, that is A1, which is equal to the m lambda s upon U1 into Ts minus T1. Similarly, A2, which is equal to amount of heat transferred in this effect, that is W1 lambda 1 upon U2 into T1 minus T2. And similarly for the A3 also. Now for the feed forward arrangement, the feed is coming in at the first stage, as well as the steam that is also coming into the first stage. So heat balance, that will be taken as W2 lambda 2. Third effect first we are taking. So W2 lambda 2, from here you will get the W2 lambda 2 and the FCPF into the TF minus T3, that will be there, which is equal to W3 lambda 3. Heat balance on the second effect, that is W1 plus lambda 1 into the flow rate difference into the Cp into delta T, and so on. While designing the multiple effect evaporation system design criteria, equal area method and minimum area methods are the two different methods. We'll be discussing the equal area method for this. Then equal heat load. Equal area method gives you the equal heat load. So heat load, that will be equal. That means the heat transferred from the one equipment will be same as that of the second and same as that of the third. So U1A1 delta T1, which is equal to U2A2 delta T2, which is equal to U3A3 delta T3. And when it's a equal area, that is A1 equals to A2 equals to A3, because when we are considering the equal area method, we are fabricating same three equipments. Your pumps, they will be of the same category, tubes, they will be of the same length. So maintenance cost reduces as we will consider the equal area for all the three effect evaporators. Then water evaporated in the overall heat transfer coefficient that will be calculated, and then the water evaporated in the effect that will be summation of W, which is equal to F into XP minus XF upon XP. So the total heat transfer area required in all the effects that will be calculated as using this FCP into the delta T plus summation of W into lambda upon P upon UE, the effective overall heat transfer coefficient, into Ts minus Tn, and this B, that is the B which is equal to 1 plus 0.1 N for the feed forward and B equals to 1 for the feed backward arrangement. Then delta T, which is nothing but the steam temperature and the that particular effect temperature. Tn is the temperature in that particular effect. So steam required for multiple effect evaporation, that is calculated by using this formula. Then the criteria for selection of the evaporator, that is the has to be considered its viscosity, the fouling cost, then the scaling, crystallization, then thermal sensitivity, evaporator load, heat transfer coefficient, and the foaming. These are the different factors that is to be considered while selection of the evaporators. Then the requirement for optimal evaporation, that is rapid heat transfer, is rates are required, low temperature operation through the application of the vacuum, then efficient vapor liquid separators you will require, then efficient energy use and recovery that will be there. Then there are certain processing factors also. These processing factors are pressure and temperature of the system that depends on the temperature sensitivity of the material and the boiling point elevation. Then the concentration of the solute in the feed, concentration of solute in the product, then the foaming characteristics and the material of construction. Then the economy of multiple effect evaporators, total kgs of water vaporized from the feed solution per kg of the original steam supplied is called the economy of the evaporators. And it's a function of the feed inlet temperature, the variation of the latent heat of vaporization over the pressure range between the first effect and the condenser type of the feed solution. These are the three different functions. Then the evaporator system used, whether it is the forward feed, backward feed or mixed feed arrangement. If the feed is at boiling point or near the boiling point, the economy in the single stage evaporator that can be the highest as 0.96. In case of a single effect evaporator, the steam economy is only up to the 0.96. However, in the triple effect evaporator, steam economy goes up to the 2.6 if the feed is at the boiling point of the above boiling point temperature in the first effect. Then the forward feed gives the better economy than the backward feed arrangement. And if the feed is cold, a preheater that should be provided to increase its temperature. But if there is no preheater and the feed is solution to dilute, then the forward feed arrangement results in the better economy. Now the last term is boiling point rise. The boiling point of water and the boiling point of solution always differs. The water contains the solute have the higher boiling points. Whenever you add the second solute, the boiling point of a water that increases. So boiling point of solution increases with the solute percentage, and as a result the difference in the boiling point of water and the solution at the same pressure is called the boiling point rise. This boiling point rise reduces the driving force for the evaporation and results in the increase in the surface area requirement.